an application of operational amplifier, and here we will convert voltage. This is a voltage to current converter. So how we will convert, we will see. So this is the schematic, and here this is the input voltage. So uh, this is the input voltage, and we are using a BJT NPN transistor, and this is our op amp. This is BJT. This is a voltage source V in, and this is VCC, the VCC of BJT. These are two resistors. This is a load resistor. These are R1. R1 is for isolation, and this is R2. So now, mm, what is I2? I2 is collector current. So I2 is V in by R2. How? So this plus terminal voltage is V in, and this plus terminal and this minus terminal both are virtually sorted. So this voltage is also V in. So this node voltage is V in. So the current is V in by R2. So this is I2. So this is the emitter current. Now IL is the collector current. So we know the relation between collector and base current. IC is equal to beta is the current gain, beta into IB, and IE is equal to IC plus IB. The both currents will be added to give the emitter current, which is beta plus 1 IB. So finally IC is equal to beta by beta plus 1 IE. And so we know that our IE is I2. IE is the emitter current, which is I2. Uh, since no current is flowing through this path. Now beta by beta plus 1 is nearly equal to 1, because beta, the values of beta are usually large, and hence we have IC is equal to V in by R2, means the load current and the load current is the collector current. So we are assuming it equal to the emitter current, which is a normal approximation in practical, means it usually happens in the lab also. So IC is equal to IL. So we started with the V in voltage, and now we have a load current IL, and with the help of means R2 we divide it. So here are the steps we need to do. Mm, Design and build the voltage to current converter given in the figure for a conversion factor of 1 milliampere output or 1 volt of input. So input voltage is 1 volt and the output voltage is 1 milliampere. So we can use that. We have to take a load resistance of 1 kilo ohm. V2 is 15 volts. Measure the voltage across R2 and RL. Compute the current in RL and R2 from step 2. Varying the input from 0 to 5 volt. Repeat steps 2 and 3. Make sure that there are at least 5 points measured per integer value in voltage value. Plot IL versus V in. Setting V in to 2 volt, measure IL. So these steps are means you can very simple. You can read and do. So this is our first part. So anyone wants to ask anything? So is it fine for all friends?
So there are two parts to this experiment. So the first part he explained, and next week we will probably, some of you will be presenting only the first part, and the complete experiment will be discussed, meaning including the second part will be discussed after the mid semester. So I will write an email to all of you what exactly needs to be done. But let's complete the complete. I mean, let's complete going through the full experiment.
Okay, so this is the second part, linear voltage regulators. So here first I will discuss this example, then I will tell what this means, this experiment means. So here this is a input voltage of 12 volt, and this is a resistance with a voltage source R2, and here suppose we have this R1 as our load resistance. So now there is a current flowing through this circuit, and with the help of that current into R1, we will get that V out. So now we are increasing the value of R1. This is our load R1. So suppose we are increasing the value of R1 from 100 to 200 ohms. Now we will see that the current value will change, and so our V out will change. So uh, we can say that the load volt means the output voltage depends on the load current. Mm, so this is an undesirable situation. We want a constant output voltage generally. Uh, so for some cases, so mm, for these for two uh, uh, so we need voltage regulator for a constant voltage output. So how will voltage regulator now means a constant voltage output. So let's see this first example here. This is a V out. This is a V out. This whole bar is at a constant voltage V out. So we will see that this V out won't change depending on the load current. It will not depend on I out value of I depend. It will not depend on I out, or we will say it will not depend on RL, load resistance. So this V out, we have the I will. So this is load resistance. This is 2N2222 NPN transistor, and this is a voltage source. There are two capacitors C1 and C2. This is a op amp, and here we have a resistance divider, and this is also a means voltage divider with the help of resistance. So uh, here the value of this value at this plus terminal is very simply we can find this uh, with the help of this voltage divider circuit. So this is VCC by R3 plus R4 is the current flowing across this from VCC to this common, and so the voltage at this junction, at plus junction, will be I into this R4. So this is the voltage at this plus terminal. So uh, similarly, this plus and this minus is sorted, so that will also be the voltage at this terminal. So now we have the voltage at this terminal. Now from other equation we can find that this V out, uh, V out, and the current through this is V out by R1 plus R2. So this voltage is like means the current is V out by R1 plus R2. So the voltage at this point is current into this R2. So we got the voltage at this minus terminal. So we can equate this V plus and V minus and get the value of V out as this. So we can see that this V out does not depend on the value of RL. It only depends on the value of R1, R2, R3, and R4, which we can choose as fixed values. So this is a linear regulator. So here we have fixed the value of R3 and R4. So we are getting means now it is only depending on R1 and R2. So this way we can play around the things. Now we have a second. We are using a 7805 IC. Two means it is a three-terminal voltage regulator. So we you can find these on the simulators as well. So here this is IN, this is IL, and this is IQ. So the IN is equal to IL plus IQ, simple by voltage law, Kirchhoff's voltage law, and then we have IQ. IQ is the regulator quiescent current, and typically in milliampere. So if the load current is much larger, we will ignore this IQ. So IN is nearly equal to IL. So what is the power? Power input is V input into I input, and V input into I input is IL plus IQ. So it is simply P out is V output by I load. So this way we can find the in efficiency P out by P in. So into 100. Um, so P regulator, P reg is the power dissipated in the regulator. So the difference between the P input and the P output. So some power will be dissipated uh, in inside this circuit, inside this IC. So now we are using some protection for this IC. Sometimes in the lab we will see that the means IC is burnt. So here we are using a protection. So like the value of V in should be greater than value of V out, so that this circuit will work properly and the current will flow this way to that way. These things. So if the value of V out at some moment becomes greater than the value of V in, so the current will start flowing in the reverse direction, and uh, there may be some problem in the circuit and IC may get burned and these things. So like how will that arise? That may arise when the charge stored in C. Yes,
No, so guys, no, hello?
yes, sir, yes, sir,
Did you know you show your document?
yes, sir.
So see this linear voltage regulator, right? This is by itself a topic in analog circuit design, and people have spent. I know many people have spent their lives designing linear voltage regulators. So this is actually not quite related to the course that we are doing, but then because it's online lab, um, we felt that this will be a relevant experiment to do. Especially, the experiment gives you further exposure to applications of op amps. So in that sense, it is valid. It is kind of justified to do this experiment. However, there are quite a few intricate theoretical details because of which the linear regulator behaves the way it is. Like for example, here what Aditya is showing is the diode, right? Now, when he shows that and says that V out can go higher than V in, does any question come to your mind? I mean, he's saying something, we are trying to show you some diagram, but any questions that come to your mind? And he also made a statement that we do not want the current to flow back into the IC, into the chip, right? Because that may burn. So why does that happen? These are complicated stuffs actually. This has got to do with device physics, and you need to understand. So I mean, I will probably explain as much as I can when you do this thing. But for now, some simplistic explanation can be, for example, in cars, right? If you are designing an electronic system in cars, um, depending on the motor that you have. So let's say you are starting your car in the morning when the engine is cold, right? Or let's say there can be failure incidents in a car. So during these kind of events when um, the motor is kind of getting a knee jerk kind of or rather behaving in a knee jerk way, there can be charge dumped onto these electronic circuits from systems external to the IC itself. So because of charges getting dumped on the output node, there will be scenarios where V out can become higher than V in. The normal question should come, why should V in the way that we are showing you the circuit, why should V in at all be higher than V in, right? There is no reason, right? In this circuit, yes, it doesn't seem like there should be a reason, but in the practical world, and the car can be a good example. Basically, in industrial electronics, if you are doing industrial instrumentation, you will see many such examples where charges can be dumped. It can be even, things like, electrical discharge of some other circuit. Some other circuit is getting discharged and it can dump a huge amount of charge onto V out, and that can create a reliability problem. So the D1 diode that is kept kind of takes care of a reliability issue. So we are not going to go into too much details, but we are going to understand the voltage regulator quite properly. I mean, in depth by doing this exercise. And please understand, he has talked about, if you go to the that in the first part of the experiment, I think we discussed, but anyway, we'll come back to that, where the BJT was shown, right? Where was the BJT current? No, not here. That current controlled, that beta thing. Yeah, yeah, I think here. Yeah, this kind of a stuff, right? Yes, yes, yes. Here, this one, right? So please understand, why a BJT is different from a normal CMOS device, meaning be it an NMOS or a PMOS, and in which place a BJT will be preferred over an NMOS or a PMOS, right? And what is the fundamental difference between these two technologies, right? Between a BiCMOS and a CMOS, right? We need to understand that. So the goal of the experiment will be to kind of be aware of the choice of instruments based on the application. So in that sense, but again, I mean, I'll not, one second, I'll not be able to, one second. You guys carry on, Aditya.
Okay, sir.
Hello? Yes? হ্যাঁ 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 করেছি হ্যাঁ। না 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 রোজডেল অপোজিট Yeah, sorry guys.
Yeah.
So the goal will be to understand the choice of instruments and their applications. And as I said, this portion, of course, I'm not covering in the theory course. But then, yeah, I mean, I think we should be able to learn something from this experiment. This is a very interesting experiment, pretty lot of intricate details, and we will take time to discuss this. Hope, and when you are actually doing this experiment in your simulator, please try to, see, I mean, the observations that you are making, right? Please try to dig deep into it and see what is going on. So Aditya will be sending this manual to the class for both the experiments today. And the first portion we expect you to definitely complete by next week, um, meaning the way we typically do, right? The next Monday. And then overall, we are going to cover both these experiments together, right? Okay. So that's all right, Aditya, on this.
No, sir. There is one more part.
One more. Okay, okay, okay. Yeah, sorry. I think
And
Murali.
I also want to add, sir, that these two write-ups has been these two documents has been written very nicely.
Yeah.
Means if like means what you said just now, that that thing is already written here. Like
Yep.
this can occur if C1 is greater than C2 and the energy storage in the output is greater. This happens when it is means like when uh, the value of C1 is greater than the charge stored here will be more and here will be less, so it will discharge more quickly to zero, and then this will become this voltage will become more than this. So means my point is to say this is like this document is written very nicely to means so that at least a third year student can easily understand these things. So no problem in that. So Okay, so this is the uh, with protection, and then we can go to the next part. So this is the voltage regulator, adjustable voltage regulator. So we can see that there here we have another resistance R2. So how this is adjustable we will see here. So IR1 is the current uh, through this resistor R, R1, and VR2 is the voltage across this resistor. So the current is IQ and IR1. So IR2 is IQ plus IR1. So VR2 is R2 uh, R2 into IQ plus IR1, and IR1 is V regulated by R1. So how is this V regulated? So V regulated is the voltage between voltage difference between this output node and this ground. So of this IC 778XX. So this is VREG. So this current is VREG by R1. This current is IQ. So VREG by I1 R1 plus IQ is IR2. Okay, so IQ is much smaller the quotient current than IR1. So we will neglect that. So V out is just we regulated R2 by R1 plus 1. So we means V out will be something plus V regulated plus V regulated into R2 by R1. So there is some minimum thing, and then we can vary it from there. So that is why it is adjustable. So V out is VREG into R2 by R1 plus VREG. So VREG plus something. So we will change the value of R2, and we will vary the V out. So this is the adjustable. So here we have the we have seen the three circuits, and here we have those three parts for that. So this is the first one which we will make manually the complete circuit. So we'll build the simulation, calculate the resistance of R1 and R2 required to produce an output voltage of 3 volts for the circuit of part 1. Minimum is 1k. So above 1k we have to choose the resistance. We'll set the VCC for 15 volts and minus 15 volts. So in this way, like uh, using RL 1k. So these things are. So one more thing I want to say is the dropout voltage in the regulator. What is the dropout voltage? So like in a regulator, the input voltage is more than the output voltage, and we have some losses in the IC and other parts of the circuit. So the difference between the input and the output voltage is the dropout voltage. So that we have to say what is the drop. So in this way we have to make it. Here also repeat of the same thing for a different uh, simulation for a different circuit. Build the linear regulator for figure 3 using 7805. You can easily get this IC if you means you will get it in LTS Spice. You can also search for other multi-sim and other, and 1k ohm register. Take note of the polarity. Uh, Vary the input voltage from 0 to 20 volts this way. So these things are there, and if you find something is written like we have also taken it from somewhere, so like you can ignore it if something doesn't make sense. Like here double check your wirings and these things. Take note of the polarity. Yes, you have to take note, but it is more meaningful when you are in a lab, like not.
Yes, yes, that's correct. It is more meaningful in a lab. You may not be able to, understand these things in a simulation environment. Correct.
So you can ignore these things. So that's all. This is a good experiment for you to do and understand. So that's all. If
Any
you have
question,
any,
guys? Yeah, any question, folks, on this? So Aditya, you will send both these experiments to the class right after. You can in that email chain that we have, right? You can
yes, sir.
circulate. Yes.
Okay, okay, sir.
Okay. So now that we have a little bit time, can we go back and look at maybe group 10, please? Group 10. Are you being there? Are you there?
Yes, sir.
Okay.
Yes, sir, I'll present.